Hello, good day to everybody. I hope you can hear me on the audience. We are just waiting 2 minutes for the attendees to join us, and we will start in a few minutes. Thank you very much for joining us today. Hello, good day, everyone. We are just waiting for some attendees to get in. We will start in about 1 minute for the webinar. Thank you for joining, and just wait about 1 minute. We will be starting. Thank you very much.
Okay, hello to each of you and welcome for joining what promises, like the first two installments in this series, to be another very content-rich webinar on dams and sustainability. Specifically today, we'll be looking at greenhouse gas emissions from dams and reservoirs. Before we get underway with the technical presentations, it gives me great pleasure to introduce Devendra Sharma to share some opening remarks. Devendra Sharma is President of the International Commission on Large Dams. He's also Vice President of ICOLD and past Chairman of the Asia-Pacific Group of ICOLD. He's been President of the International National Committee on Large Dams for 2 terms, from 2018 to 2020, and also from 2020 to 2022. Mr. Sharma has 44 years of experience in water resources and energy sectors in India and abroad, and has received 9 national awards. I believe that's actually 10 now as of last week, with more than 53 publications to his name in international journals and conferences. So over to you. Thank you, Mr. Sharma.
Thank you, Steve, for that wonderful introduction. So, friends, as you are aware, recently ICOLD has come out with World Declaration on Dams and Reservoirs. It was approved in New Delhi on 3rd October 2024 and has been signed in Chengdu on 20th May 2025. It highlights the key role of dams in climate change adaptation and energy transition. In parallel to this declaration, as you might be knowing, ICOLD launched the Dams and Sustainability Initiative in 2023, bringing together the efforts of several technical committees of ICOLD. ICOLD's Dams and Sustainability Initiative aims first and foremost to raise awareness among dam professionals of the need to improve the sustainability and life cycle thinking of existing and new dams. ICOLD is fully committed to a sustainable future. ICOLD board strongly support this series of webinar and other activities planned by ICOLD Dams and Sustainability Working Group. Central Office of ICOLD is also completely supporting this initiative of D&S Group. To date, the ICOLD D&S Group has organized 2 webinars. Most of you might be aware See, the first one took place in May 2024 and presented the main sustainability goals and objectives of this new ICOLD initiative. The second webinar was held in May 2025, introducing life cycle sustainability assessment methods and providing examples from other sectors that could be appropriate for assessing the sustainability of dams and reservoirs. See, if you are interested, full videos of both webinars are available on the ICOLD website. You can see these from ICOLD website. Next. This webinar 3, which is today, it will focus on calculating greenhouse gas emissions throughout the life cycle of dams. GHG emissions are main cause of global climate change. Researching and calculating GHG emissions is essential to identify potential areas for emissions reduction in all human activities, including dams. ICOLD has invited a distinguished group of speakers to present this important topic, beginning with the general introduction and then moving on to more specific aspects related to greenhouse gases emission associated with dams and reservoirs. See, let me share with you, because of the climate change disasters, we have seen many failures. And recent one in India is about the failure of concrete faced rockfill stage 3 Teesta Dam, which failed due to glacial lake outburst on the night of 3rd October and 4th October. You can see in the pictures what the disaster has taken place. Next. Well, towards the end, I would like to express my gratitude to the organizations actively cooperating with ICOLD in this webinar, especially to the GHG Protocol, the GRES tool, and the University of Québec in Montreal, the China Institute of Water Resources and Hydropower Research, Aqua-Consult, Bluemethane, the ICOLD Technical Committees D, Technical Committee T, and Technical Committee Y that are actively participating in this webinar. Hydropower and dams for moderating the session. Most of you might be knowing our friend Steve Usher. He's from Hydropower and Dam. SpanCold for their technical support. And we have a very active member from SpanCold organizing all these activities. Next. I wish you all a very successful and fruitful webinar. Thank you all for being part of this important webinar. And now I hand it over to the organizers to take it forward. Thank you.
Thank you, Mr. President. Steve, please.
Thank you. Thank you, Devendra, for those introductory words, setting the ground for today's webinar on greenhouse gas emissions from dams and reservoirs. As Devendra just said, my name's Steve Usher. I'm the Deputy Editor of the Deputy Editor and ESG Manager at Aqua-Media, which is the publisher of the International Journal on Hydropower and Dams. I previously worked as the ENS Programme Coordinator for the Nam Thun 2 Hydro Project in Laos, and separately for various UN climate projects throughout Asia. More recently, I've served on various ICOLD technical committees, and I'm very pleased to be moderating today. As was just made clear there and reiterated by Mr. Sharma in the first two webinars, sustainability is one of the most important topics influencing the support or indeed the opposition to dam construction worldwide. And with an increasing focus on climate change, I think it's fair to say this concern can be expected to continue into the future. So the first webinar was an excellent opportunity to explore the main sustainability goals and objectives of the ICOLD initiative. And the second webinar introduced tools and methodologies that can be applied to assess the life cycle assessment sustainability of dams and reservoirs. And as a reminder, archived videos of both of the previous webinars are available for download via the ICOLD website. This third webinar will focus on calculating greenhouse gas emissions throughout the life cycle of dams. And just before I hand back over to Francisco to run through the objectives and purpose of today in more detail, just mention a few brief housekeeping messages. Firstly, we expect the webinar to again be fully interactive, and we encourage anyone with questions to please use the chat facility within Zoom to post them there. Hopefully, you can see, I think towards the bottom of your Zoom app, or if you're on the browser, there is a tab which says chat. If you click on that, there should be a panel opening up. If you post the questions there, myself and the speakers will be able to have access to those. At the end of the final presentation, we'll have 20 minutes or so where we can run through as many questions as possible. So please make use of that. Without further ado, let's get underway. I will introduce now the first speaker who's been instrumental in organising not just this webinar, but the previous two webinars, and also the ongoing research at ICOLD into sustainable dams. So I'm very pleased to introduce Francisco Ortega. Francisco is an international specialist in the design and construction of concrete dams. Since 1999, he's been running Fosce Consulting Engineers, which is based in Germany. He's a member of both the Spanish and German national committees on large dams and represents these two countries in the ICOLD Technical Committee P, dealing with cemented materials dams. In addition to this, he's leading the preparation of the second volume of the Sustainability of Concrete Dams with Technical Committee D of ICOLD, and leads this ICOLD Dams and Sustainability Initiative. So over to you. Thank you, Paco.
Thank you, Steve. Thank you, President Devendra Sharma, for introducing this webinar and for your continued support. Thank you to all of you for joining us today in this third webinar organized by the ICOLD Dams and Sustainability Initiative. The ICOLD Dams and Sustainability Initiative has two fundamental objectives: to continue to raise awareness on sustainability among our dam community, and to better understand what it means and how to account for it. The framework is to be in line with the United Nations Sustainable Development Goals, and the challenge is to address all aspects of sustainability: economic, environmental, and social aspects. Furthermore, we try to develop an approach that should be, in our opinion, practical, resulting into feasible steps with tangible impacts on design and construction, auditable by implementing quantitative metrics as far as possible for clear assessment, and finally sensible, taking into account the entire life cycle for a holistic planning. This is the brief roadmap to date of the initiative. We began our journey in mid-2023 when the ICOLD board launched the initiative, and continued with the various meetings at our annual conferences in ICOLD, as well as online meetings. As our president mentioned earlier, we have held two webinars today. Today's webinar is the third, in which we will discuss greenhouse gas emissions during the life cycle of dams and reservoirs. Steve's first presentation will raise our awareness of climate change and the impact of different concentrations of greenhouse gases under different future scenarios. It is an introduction that will motivate us to identify and reduce emissions throughout the life cycle of dams and reservoirs. The GHG Protocol is the most widely used greenhouse gas accounting standard by companies worldwide. Alejandra will introduce us to it, with a special mention of the land sector and removals standard, which has a specific application to reservoirs. ICOLD's Technical Committee D is working on a study on GHG emissions throughout the life cycle of dams and reservoirs. Marco, chair of this committee, will present the current status of the work and future plans for its development. This presentation will give us thorough understanding of the impact of dams that they have on emissions throughout their lifetime. Maud's presentation will focus on biogenic emissions produced in reservoirs. She will begin by explaining the scientific basis, and then go on to detail where and how to obtain data on emissions in reservoirs, as well as ways to reduce them. The next presentation is about the GRES tool. The GRES tool is internationally recognized for estimating net emissions attributed to the creation of reservoirs. We are fortunate to have Yves, its developer, with us in this webinar, who will explain its history, its use, and its future development. The next presentation will focus not on the reservoir, but on estimating GHG emissions during dam construction and how different types of dams affect emissions. It is based on the work we are developing at ICOLD based on the experience in dam design and construction methodologies. The following presentation outlines a possible way to reduce emissions through the capture, removal, and potential use of methane produced in reservoirs. To this end, we have invited Bluemethane, a pioneering company in this field, to explain its promising technology and future application. Last but not least, we are fortunate to close this webinar with the participation of the China Institute of Water Resources and Hydropower Research, which will present the decision-making system for calculating the life cycle carbon footprint of dams in China, and in particular, its challenges, framework, and support system. I hope and wish you enjoy the webinar. Thank you very much for your interest. And I hand over now to Steve to present the technical speakers. Please, Steve.
Thank you, Paco. Okay, hopefully you can see my slides there. So as Paco just mentioned, I'll be briefly summarizing at the macro level some of the key climate change science and current global situation. The science, I think, is well established, linking anthropogenic greenhouse gas emissions with atmospheric concentrations of greenhouse gases and global surface temperature increases, approximately since the European Industrial Revolution in the mid-19th century. As the lower left graph here shows, greenhouse gas emissions have been increasing significantly since the Industrial Revolution and continue to increase today. These emissions have led to increased concentrations in the atmosphere of major greenhouse gases, in turn increased global temperatures, as shown in the top right there. So it's very plain to see this is taken from the most recent IPCC AR6, which was published in 2023. The very close synchrony between emissions, the concentrations in the atmosphere, and then the temperature increases. As this report shows, and as it states, the 1.1 centigrade global warming observed in the period 2011 to 2020 is unequivocally caused by human activity, and warming is likely to reach 1.5 degrees within the next 5 years if emissions are not rapidly and deeply cut, requiring a phase out of fossil fuels and significant and immediate action to avoid increasingly dangerous climate impacts. So that's a statement taken from the 2023 IPCC AR6 synthesis report. The same relationships shown on that previous slide have helped to inform climate models to project future climate change based on different emission scenarios. And over the past few years, international multidisciplinary teams have developed a range of pathways that examine how society, demographics, and economics might change over the next century. These shared socioeconomic pathways are climate change scenarios of projected socioeconomic global changes up to the year 2100, with the main 5 SSPs shown here. Each SSP is used to derive greenhouse gas emission scenarios with different climate policies and provide narratives describing alternative socioeconomic development. The SSPs are also being used to explore how societal choices will affect greenhouse gas emissions and therefore the climate goals and how they could be met or perhaps missed. The number after the SSP prefix represent different levels of radiative forcing in watts per meter squared up to the end of this century compared to the benchmark year of 1750. Radiative forcing refers to the change in the net energy flux, that's incoming minus outgoing radiation, at the top of the atmosphere due to external factors, including greenhouse gases. So in the lower left, SSP 1 to 1.9 and SSP 1 to 2.6 are the low and very low emission scenarios, with SSP 1 to 1.9 being perhaps closest to the Paris Agreement target of limiting temperature increases to 1.5 degrees. SSP 2 to 4.5 is the intermediate or middle of the road scenario, roughly equivalent to 4.5 watts per meter squared of heating. And the SSP 3 to 7 and SSP 5 to 8.5, these are considered the high or very high emission scenarios, representing significant radiative forcing levels of 7 and 8.5 watts per meter squared, respectively. The 5 SSPs shown on that previous slide are used to derive greenhouse gas emission scenarios under different climate policies. And while the latest IPCC report, AR6 synthesis report, doesn't estimate the likelihood of the different SSPs, I think it's fair to say that anecdotal information does not seem to support achievement of the Paris Agreement to limit the temperatures to 1.5 degrees. For example, SSP 3 listed here is characterized by regional rivalry, resurgent nationalism, and regional conflicts, which I think, if you pick up any newspaper today, ring very true. In January this year, the US President Donald Trump signed an order to withdraw from the Paris Climate Accord. And in the UK here, the leader of the opposition has also said in the past 2 months, they plan to repeal the UK Climate Change Act, which is our own legislation to meet climate change goals, if they, the Conservative Party, win back power. Separately, a recent study from the London School of Economics found that despite climate pledges, most firms are delaying action and underfunding real transition strategies. That same study analysed disclosures from 2,000 publicly traded firms worth about 87 trillion US dollars and found that only 2% of them had shifted capital away from high carbon assets. Additionally, separate reports released this year by Morgan Stanley, JP Morgan Chase, and the Institute of Finance all make clear that the finance sector considers the Paris Climate Agreement to be effectively unachievable. In one report in March 2025 by Morgan Stanley, they state that we now expect a 3-degree heated world and advise investments be made, for example, into air conditioners rather than alternatives. So tomorrow is scheduled to be the concluding day of the COP meeting in Brazil. Traditionally, this week coincides with the release of major climate-related reports from various international authorities. And although the final communique has not yet been published, I just finished with this slide highlighting some of the key messages. The UN Secretary General Antonio Guterres has noted that under current plans, even if they were fully implemented, the global temperatures are set to increase by about 2.3 degrees. And it's worth noting that Chapter 11 of the IPCC AR6 states that while it's low confidence regarding the levels at which possible change associated with global and regional tipping points occur, these extreme changes cannot be excluded, especially at high global warming levels. Separately, the WMO released a report confirming that greenhouse gas emissions have risen to a record high, with this year again looking to be one of the hottest on record. And as noted there, all 10 of the hottest years measured have taken place in the last decade. Finally, looking forward, until the release of the World Energy Outlook last week, all of the previous IEA modelling scenarios assumed that fossil fuel consumption would peak this decade. But in its latest analysis, published just last Wednesday, the body whose research helps to shape global energy policies said that if the world continued on its present trajectory, oil and gas demand would continue to rise for the next 25 years, and there'd be no meaningful fall in CO2 emissions. So the implications of these reports and the different SSP scenarios outlined earlier will have significant implications undoubtedly for the hydropower and dam sectors, as the duration, frequency, and intensity of extreme weather events, including floods, droughts, and storms, is likely to increase. So, on that cheery note, I'll hand over to the next speaker, Alejandra Bosch, who will be describing the work being undertaken by the Greenhouse Gas Protocol. Unfortunately, as Paco already mentioned, due to travel commitment, she's unable to participate live today, but has kindly prepared this pre-recorded video presentation. Alejandra is a land sector associate at the Greenhouse Gas Protocol, where she supports the development and implementation of the Greenhouse Gas Protocol land sector and removals guidance. She's previous experience in developing the forest and tree sectors of the greenhouse gas inventory for cities in Latin America, as well as strengthening green infrastructure, natural capital, biodiversity, and urban development projects.
Ok, Alberto, cuando quieras.
Of the land sector team within the Greenhouse Gas Protocol. And today I am going to share with you a quick overview of who we are, the accounting approach that we use in the land sector and removal standard, and also how we address reservoir emissions within the LSR standard. The Greenhouse Gas Protocol is a partnership between the World Resources Institute and the World Business Council for Sustainable Development. We develop standards and guidance that help companies measure, manage, and report their greenhouse gas emissions, as well as keep track of their progress towards their targets and to reduce their emissions. We provide the world's most widely used greenhouse gas accounting standards for companies. And we develop these standards through an inclusive global multi-stakeholder process that includes representations from business, academia, governments, and NGOs. The land sector and removal standards follows an inventory accounting approach, which tracks greenhouse gas emissions and removals within the company's or the organization's boundaries. We have different approaches for a company to define what we call operational or organizational boundaries, which is essentially understanding the activities that are within their operations or control and that generate direct emissions, and the activities that are within their value chain and therefore generate indirect emissions. The direct emissions, we call them Scope 1 emissions, and the indirect emissions can be Scope 2 if they were generated from electricity that the company consumed, or Scope 3 if they are generated due to other activities that occurred outside of the company's control or operations, so within the company's value chain, essentially. For example, if a company owns land, the emissions and removals that occur within that land would be their Scope 1 emissions or removals. If another company does not own land, but they purchase a product or a service that was grown or generated in land, then those land emissions would be associated with that product or service, and then they would be in the company's Scope 3 emissions. Scope 3 emissions are related to the life cycle of a product or service and are then subdivided into different categories according to the upstream or downstream activity that generated such emission. So, for example, category 3, which is fuel and energy related activities, are relevant to hydropower reservoir emissions. So a company that consumes or purchases energy that was generated by hydropower would then report the emissions related to the reservoir in their Scope 3, Category 3. Corporate inventory accounting, as well as reporting emissions as either Scope 1, 2, or 3, is the approach that some of our standards and guidance are based on, including the corporate standard, the Scope 3 standard, and land sector and removals standard. We published a draft of the land sector and removals guidance in 2022, and the final version of the LSR standard will be published in December. So please stay tuned and subscribe to our newsletter, where we will publish more information about our launching date. The LSR standard and guidance will cover land management and land use change emissions, CO2 removals and storage, and biogenic products and technological removals-based products. It is relevant because it provides a framework to account for greenhouse gas emissions and CO2 removals related to the land sector, Although just a note that this version excludes removals with storage in ocean or freshwater carbon pools. The standard also provides guidance to set targets and track progress, and it is expected to be used by key initiatives like the CDP and the Science-Based Initiative, the Science-Based Targets Initiative. I want to expand a bit, specifically on land use change emissions, because they are relevant to water reservoirs. Land use change emissions are generally released to the atmosphere quickly following the conversion event. But a land use conversion can enable a continuous production or provide a service, not only during the following year, but for many, many years. So therefore, an assessment period is defined in order to assign the emissions generated due to the land conversion event to the products or services that are provided in that land during the period that follows the land use change event. So, for example, when it comes to agriculture, most crops would be associated with an assessment period of 20 years. This means that if a company purchases a crop that comes from a field that was deforested within the past 20 years, then that company would have to account for a portion of the land use change emissions that occurred in that field because they are associated with the life cycle of that product. To define what portion of the emissions the company has to account for, we follow the method of linear discounting, which means that companies sourcing from land that was recently deforested would account for a larger portion of the total land use change emissions than companies that are sourcing from land that was deforested a longer time ago, like closer to 20 years ago. And to finalize this presentation, I want to speak specifically about how we address reservoir emissions in the land sector and removal standard, which is a result of all the feedback we received and the input of our technical working group members that was formed by experts of this field. So it was defined that most of the greenhouse gas emissions of water reservoirs are due to the flooding event, so the land use change event, and are not so much related to the management of the reservoir. It was defined that CO2 emissions would have an assessment period of 20 years, and methane emissions would have an assessment period of 100 years. This means that total CO2 emissions due to land use change event are divided and reported across 20 years, and total methane emissions due to the land use change event are divided and reported across 100 years. So the company that owns the land or operates the infrastructure would account for those emissions within their scope 1, but these emissions would also be reported in the scope 3 of companies that are purchasing services generated in that reservoir. For example, companies that purchase electricity generated from hydropower, or companies that produce or purchase agricultural products that are irrigated with water stored in water reservoirs. These companies would have to find out if they are sourcing from a reservoir that had a land use change event and account for a portion of the emissions depending on how recent that land use change event was. And more details about this will be published next month in the Land Sector and Removal Standard in December 2025. And thank you so much for listening. Please feel free to reach out if you have any questions.
Great. So Alejandra, I don't believe we'll be able to join the live Q&A session following the presentations today, but if you do have any questions for her, please feel free to drop them to myself or Francisco or Marco via the email address which Francisco will be showing later on, and we'll be sure to pass them on and get back to you with those. The next speaker is Marco Conrad. He'll be speaking on some of the work he's undertaking to assess the life cycle greenhouse gas emissions from dams. Marco holds a PhD in civil engineering and is principal dam engineer at Afry, Switzerland, with more than 25 years experience there. His general work focus is on the design, construction, planning and supervision, surveillance, condition assessment and rehab of dams and mass concrete structures. Marco serves as the ICOLD Technical Committee on Concrete Dams and is a key part of the coordination group for the ICOLD's initiative on dams and sustainability. So thank you, Marco.
Still mute. Thank you, Steve. And hello to everyone. So thoughts are still cruising around on this topic. So I'm only able to show a very small amount of worked examples here, but nevertheless, I would like to introduce the topic of life cycle GHG emissions of dams here. Now, does it work? Okay. So the determination of life cycle GHG emissions from a dam and reservoir system is performed through the method of life cycle assessment, or LCA. In short, LCA can generally be defined as a systematic process for evaluating the environmental aspects and potential impacts associated with a project, service, or civil infrastructure, etc., throughout their life cycle. Carbon footprint assessment, or CFA, is a specific subtype of life cycle assessment that focuses only on the environmental aspect of GHG emission and the impact of global warming potential. Principles of LCA are addressed in the ISO 14040 family of standards, and carbon footprint assessment is more specifically addressed in ISO 14067 standard. The LCA typically follows a standard concept of steps, starting with the goal and scope definition phase, in which the study objective is defined. In our case, this would be determination of GHG emissions of a dam and reservoir, for example, for the comparison of options. System boundaries will be defined depending on the objective of the study. And this also serves the definition of a functional unit that is used in the comparison exercise. The next step, very, very important, probably the most important step in the LCA, is the inventory analysis phase, which is essentially the data gathering, collecting of information, and the quantification exercise. In other presentations later, emission factors will be addressed. I very briefly addressed that in my presentation here. So this step is then followed by the actual impact assessment phase, and the LCA closes with the interpretation and discussion phase, in which uncertainties, scenarios, etc., are addressed. So currently, there is no single specific and generally accepted standard for LCA and CFA of dams and reservoir projects in their different planning and life cycle phases. At the moment, And until such standards will be available, a multi-tool approach is proposed, and essentially that is covered in today's presentations. So one would be the GHG assessment for reservoir system using the GRES tool that is presented later on. And the GHG assessment for the project structures and components could use either the simplified functionality that is available within the GRES tool, or a detailed LCA approach based on the bill of quantities and specific emission factors for the implementation stage, and based on credible scenarios for the operation and end-of-life phases. So if we talk about lifecycle GHG, what actually is it, what we are talking about? Lifecycle GHG is also known as whole life carbon. In our case, lifecycle GHG is the indicator quantifying the greenhouse gas contributions of the dam and reservoir along its full life cycle, included embodied carbon and operational carbon related to the core infrastructure and the core process. So the core process can, for example, be generating hydropower or simply storing water. And this definition of the core process actually determines which project components or which core infrastructure needs to be considered in the carbon footprint assessment. So for hydropower, for example, the generally applied rules consider 100-year lifetime of the project without decommissioning. But reinvestments within the 100-year lifetime period are considered, and those are typically considered based on the design service lives of the different components. So electromechanical also is probably renewed all 60 years. The civil structure, or especially the dam, is not considered with any refurbishment or so during its lifetime. So those are all different assumptions that play quite a role in the accounting of the emissions. And if we look at the system boundaries related to the actual scope of our carbon footprint assessment, it becomes quite clear that there will be differences in the system definition depending on, or boundary definition depending on the actual objective of the study. If we look at the carbon footprint of the full project, for example, a hydropower project, then actually the study would comprise all the components that are related to the core process of generating hydropower. That's the dam, the spillway, the reservoir, waterways, powerhouse with the generating facilities in there. If our objective is the comparison of the greenhouse gas footprint from a dam type, for example, then the system boundary will reduce, and we would probably, because the reservoir is there anyway, would look only at the dam structure with the related major components that have to be considered for the different type of dams. So that I want to illustrate briefly with that or those images. Like different dam types, for example, require different concepts of spillways, and the integrated system of dam and spillway system that's required for the different types of dams. That is what has to be considered in the core infrastructure. So it would be a totally misleading comparison if we would look at only the rockfill in the case of a rockfill dam, for example, and look at the specific footprint compared to the specific footprint from a concrete dam, where the spillway is easily integrated into the dam body. If we look at the different processes in the implementation phase of a dam, for example, we need to consider all the material flows, and the typical example here would be the quarry, for example, in which for either the rockfill in case of rockfill dam or aggregate in the case of a concrete dam, a lot of quarrying is required, including explosives, and the quantities of material are quite different. Quantities of explosives are different, and that has a major effect on the outcome of the carbon footprint. So the explosives are actually a very good transition now to the topic of emission factors that are used in a carbon footprint assessment. So emission factors are applied to convert activity data, for example, production of 1 ton of rockfill or aggregate, into the greenhouse gas emission. So let's stay with the example of explosives. It would be the greenhouse gas emission from the manufacturing and combustion of 1 kilogram of explosive, for example. Emission factors are geographically and temporally very sensitive. So depending on where we have the project and when we have the project, the emission factors can vary quite a lot. So especially during early project phases, the definition of those emission factors is not easy, and there are a number of databases that can be used to support the specification of those emission factors in analysis that we want to do. Very good, for example, is the IPCC database that holds a lot of data that is also geographically delineated, and so is very valuable for us for looking at projects in different geographical areas or different countries. In worked examples, we see that the project-specific greenhouse gas intensities can vary quite greatly, and the main contributor can be the reservoir, for example, in one case, and in other cases, it may well be the implementation of the project. If the reservoir, for example, is not emitting substantial greenhouse gas during the lifetime or service period of this project. So it's incorrect to say that greenhouse gas emissions generated in the implementation phase are always smaller than those generated in the reservoir. That's an assumption that is heard quite often, but it is not necessarily correct. So anyhow, all this points at the need to consider the full life cycle of dam reservoirs if we want to properly compare greenhouse gas emission footprints from different dam types or projects and so forth. This is another example, another worked example from a feasibility stage project comparing an RCC dam configuration, so including all the project components, spillways, the water conveyance structures, and so on, and comparing this with a concrete phase rockfill dam option, including the same project components. And it is quite interesting to see here that it is very important to look at the total greenhouse gas emissions compared to only the intensities. So in that example, the RCC dam option, for example, comes at a much lower carbon cost or carbon emission compared to the concrete phase rockfill dam option, whereas compared to the unit of dam volume, the picture is exactly the other way around. So what we can conclude from that is that we, especially for climate change mitigation issues, we need to look at total carbon footprints and not only at the unit or specific emission values. When looking at carbon footprint assessments or life cycle assessments of dams and reservoirs, we have quite a number of challenges or dilemmas, as we call them. One is that each dam project is unique, and we also have multi-purposes often involved in the projects. We deal with very long service lives of dams, and there's clearly the question whether 100 years is as a service period or lifetime period is the number to go with. It is sometimes a challenge where to draw analysis boundaries and how to consider boundary conditions that would have a serious impact on project service life or lifetime in general. Like, for example, issue of sedimentation here is quite an important aspect. We often have a lack of data or information and do not exactly know in early project phases about the performance behavior that plays a role in decision making in the project. Now, important notes on life cycle considerations.
Marco, please,
yeah.
Excuse me if you could go to conclusions. We are running out of time. Thank you.
So what we focus on is hotspot identification in the life cycle assessments rather than perfect correctness of data and assumptions. Anyhow, what's the motivation to do this LCA? It is all voluntary. There are no mandating policies, so to say, or global standards that mandate businesses to abate their GHG footprints. Maybe it's part of business models that are incentives for businesses to go that way. So it's very much about the mindset and vision, with focus on long-term consequences rather than short-term reactions, looking at the short term of projects. And it can be quite healthy to look into the long term. It is an opportunity to produce better projects and look at long-term benefits. And we discover a lot of things when we look towards the end of life of such projects. Thank you very much.
Great, thank you, Marco, for those very interesting comments, and look at life cycle analysis with key considerations, including emission factors. Some of these topics will come up again in the next few speakers' presentations. I see already there are several questions coming in, which is great. Just a reminder, please, to use the chat facility for this. And after the final speaker today, we'll have 20 minutes or so, I hope, to run through as many of these as possible. Next speaker, we have Demarty, who will be reporting on the collection of greenhouse gas emissions data from reservoirs. Maud is a biologist with 25 years of experience, and she earned her PhD in limnology, where she studied the carbon budget of lakes. She subsequently conducted comprehensive studies and surveys worldwide on the subject. In September 2019, she established Aqua-Consult, a company specializing in innovative aquatic studies, and she serves as vice chair of the ICOLD Committee Y on climate change, dams, and reservoirs. So over to you. Thank you.
Hello, everybody. Can you hear me? Yes, great. Thank you, Francisco. So thank you to invite me today. I'm very glad to be with you, and I will make a short presentation on collecting data of GHG emission from reservoirs and tell you how relevant it is and how efficient it can be. Yes, so the objective of measuring the emission is to get the carbon footprint of reservoirs. So it corresponds to know, in other words, if the transformation of the landscape lead to a loss or a gain in carbon sink capacity at the watershed scale. For example, here, from a river to a reservoir. So among the impact of a reservoir creation, which are numerous, there are modification of the biological processes, release of nutrients in the water column, increase in productivity and biomass of plankton and bacteria, and all that things can lead to a peak in GHG emission related to the organic matter decomposition. So there are three types of emission currently measured in aquatic ecosystems. First of all, the diffusion that simply results in the equilibration of greenhouse gases concentration at the air-water interface. We also account for the degassing, which is also diffusive emission, but that occurs because of the strong turbulences in rapids in natural ecosystems or downstream of the generating station after turbines and spillways. We also account for ebullition, which is mainly produced by CH4 accumulation in sediments in shallow waters. So it is estimated that around 1 million dams have been built over the years on rivers and streams worldwide. Of course, it's not possible to study all these ecosystems, but for the largest reservoirs, it's important to include this emission in LCA or carbon footprint assessment, as Marco mentioned just before me. So in that objective models like the GRS tool aims to reach that goal. But the problem is that models need real data, in situ data. So one of my message today is that the industry needs to get involved in that data collection to allow all the community to figure out what emission will be occurring in the next years. So there are some famous studies in the world on special reservoirs that were very well studied. We can mention the Isthmian 1 reservoir in Canada, the Three Gorges reservoir in China, or also the Petit Saut reservoir in French Guyana. So these reservoirs have been deeply studied with multi-years sampling campaigns, more than 10 years, which is a lot of job and a big budget, numerous sampling stations, and work plan that allowed the stakeholder to understand the processes occurring in the reservoirs and in the landscape. And also it was necessary to have a strong collaboration between industry, university, and local people to achieve these big studies. But it's not mandatory to go so deep, to invest so much, to be part of the world database. You can make your part without such big budget. So as an industry, as a reservoir owner, your objective is to get a snapshot of your reservoir emission, to be able to define in which range you are. So are you a strong emitter of CH4 or CO2, or your reservoir has only small emission? So in getting real in situ data, you will be able to compare your system with other ecosystems. And also maybe to focus on what are the main sources of emission. You will be able to better document national inventories and also adapt and mitigate your emission. And of course, increase the international knowledge and increase the sensitivity of the model, like the GRES tool. So how do we get in situ data? The main point of my message is that it's very important to follow the guidelines that already exist to be able to have strong, reliable measurements on site. So up to now, the best way is to follow the guidelines that you see here, produced by IHA and UNESCO more than 15 years ago, but it's still valuable. So on site, we go for diffusive emission measurements. We go on site, so on rivers, reservoirs, and in all the landscape, and which means a lot of work. Of course, we propose to sample at least 3 stations, for example, on a reservoir, which is not a lot, but still it's a lot of organization. Under certain conditions, we can have an idea of the GHG concentration of the reservoir by sampling the water inside the scroll case of the generating station. This is also the sampling station that is used to estimate degassing. So the degassing emission can be estimated at a single sampling point. For the evolution, you will be obliged to go on site, which is a little fun. So in the littoral area of the reservoir, so that's where the bubbling occurs. So I mentioned the reservoir, but also it's very important to sample lakes in the regional lakes around your reservoir, because this is the only way you can really attribute the emission to your reservoir by comparing what is occurring in the watershed. So how do we get the data from the GHG emission from aquatic system are measured since 30 years now, and in the past decade, the evolution of sensors allowed important progress in sampling efficiency. So for diffusive emission, getting some direct flux with floating chambers is still a plus, something very interesting. But we should admit that currently we are more focusing on gas concentration in the water column, and so flux calculation from this concentration. So with the improvement, we are able to sample, to measure gas concentration simultaneously at the surface and bottom of a reservoir, for example. And we can also have automated system on raft at the reservoir surfaces that allow us to have a very long time series of gas concentration, and so seasonality, etc. So it's very interesting. These automated systems can also be installed inside generating station, as we also currently have in Québec. And it was done also in France, California. So it's been done at more than 15 places right now. And this allows continuous measurements of gas concentration of the water flowing through turbines. So that allows us to calculate hourly or daily fluxes and degassing. and it can be deployed for several months or years. So finally, for evolution, the main method is to use simple funnels, but recently we design automated traps that collect bubbles as they occur, and also directly measure CH4 concentration in the bubbles. So it is continuous measurements, and it allows measurements for several months, which is very interesting. So the question is often if it's possible to reduce emission from reservoirs. So you may have understand that it's a multi-scale problematic because we are talking at the watershed scale. So not only the reservoir, but also lakes, forests, rivers. So it's necessary to understand where the problem comes from. And also, it's difficult to have the boundaries of the time scale of the follow-up. So the best chance to reduce the emission is finally to not produce the emission. So to have a strong design of the project with promotion of a project with more than 5 watts per square meter of productivity. And that's what we can find in valley type reservoirs, for example, rather than dendritic reservoirs that can emit a lot. The aeration at the turbine outlets and spillway can be a solution to transform CH4 in CO2, and so to reduce the amount of emission in CO2 equivalent. And it's also possible to play a little bit with the water intake depth, so reducing the CH4 that you pump at the bottom of the reservoir. So what is very important also is to account for climate change effects on hydrology, water, and sedimentation, sediment quality and quantity that arrive in the reservoir. So it's a lot of job, but as I mentioned, getting a snapshot of a lot of reservoir will be a very positive thing for the reliability of the models that we can all use afterwards. So thank you for your attention, and I'll be pleased to answer the question.
Thank you very much, Maud. Continuing this theme, the next presenter in our talks today will also present analysis of greenhouse gas emissions from reservoirs and speak directly to the GRES tool that's been developed for this purpose. Yves Prairie is Professor of Limnology at the University of Québec in Montreal and a founding member of the GRIL Research Centre, which is a multi-university research centre in limnology. He held the UNESCO Chair in Global Environmental Change from 2011 to this year and was President of the International Society of Limnology. Yves is also a Fellow of the Royal Society of Canada. So over to you, thank you.
Thank you, Marco. See, you should be able to see my presentation. And yeah, thank you for the invitation. I'm here to speak a little bit about the GRES tool, its history, its current use, and its future development. And so the GRES tool was actually initiated in a workshop. I think it was even before 2010, maybe 2008, that was organized by the International Hydropower Association. And basically, my task after that meeting was to start pulling data together, whether to create some sort of tool, a screening tool. And the aim was simply to identify reservoirs that had potentially high emitting. It's just to distinguish between, okay, this is a low emitter, this is a medium emitter, and this is likely a high emitter. But we continued in that direction, and in the 2012-14, we collected all the data basically that was published in the primary scientific literature. And we built empirical models to try to put together, using a consistent methodology, functions or empirical relationships that allow us to predict GHG emissions through various pathways. And this has led, therefore, to the GRES tool that you see here, the first page on the web. It's a completely online tool. And basically, you enter a whole bunch of data about the reservoir and the watershed, and you get a table with projected emission over a 1-year life cycle. And you also see it in the bottom here, kind of the temporal evolution of these emissions. That is, emissions right after flooding of a new reservoir will be higher than after 100 years. But what's behind the tool? The tool, basically, what it attempts to do is to quantify only the GHG emissions that are attributable to the reservoir creation, not all of the emissions that actually are occurring at the reservoir site. This is kind of a complicated, but this is what it attempts to do. One of the things that it attempts to do. And as I said before, it follows a very globally consistent approach. The data sources are the same everywhere you apply the tool in the world. So basically, as I said, these are empirical functions, and here are simply kind of the illustration of the main factors embedded in those empirical functions. So the age of the reservoir, the temperature, the soil, the amount of carbon in the soil that was flooded, and that's useful for predicting carbon dioxide emission. Same thing for a methane, although the shape is slightly different of the relationship. But again, reservoir temperature are important factor, and also the extent of the littorals. This is particularly important for methane emission. So how has the tool been used so far? Well, I think there are 3 main user types for the tool: the industry, government agencies, and the scientific community. So for the industry now, the GRES tool has over 3,000 registered users from 118 countries. Here you see the global distribution of the users. The darker the color, the greater the number of users. So this has clearly taken on, but it's only one segment of our user. The other user is governmental agencies. And why is that? It's because since the publication adoption of this IPCC methodology report in 2019, now countries have to report reservoir emissions in their annual national inventories. And right now in Canada, the Canadian government is using the GRES tool to try to get the best number they can at the moment to establish the total emissions from reservoirs in Canada. And the third user type is the scientific community. And here's an example where we've been able to use the GRES tool and try to get an estimate for all the major dams in the world, so as to localize, to situate geographically, okay, where are the hotspots of GHG emissions from reservoirs. And in a different study, the GRES tool was also used to look at what was the temporal evolution. Of course, the temporal evolution of reservoir emissions followed the construction of the reservoirs. And because, as I said earlier, the highest emission when you flood a reservoir is right after the flooding, and then it decreases. Well, you can see that, in fact, the peak of emissions from all the reservoirs globally was reached in the mid-1980s. And so the peak of reservoir emission is behind us. Even if we consider the future projects that are in the pipeline, so to speak, we see that we are projecting a continued decrease. This is the time course of emission, but it's important to note that the peak effects of these emissions on climate occurs about 20 to 25 years later. So you have to take that into account. But perhaps more interesting for you, because I think a lot of you have already are aware of the GRES tool, is what are the future developments of the GRES tool? And as I said earlier, the current GRES tool was based on all the scientific publications up to about 2016. And these were used, the data that was extracted from those publications were used to develop the models. But since 2016, we have 80 to 100 new scientific publications with measured data of GHG emissions. So right now we are compiling all this data and compiling all the ancillary input data, and we are expecting to develop new models in 2026 when this extraction of all the new data will be complete. So that's one thing. The second future development is what I think is there is a need for a complementary and more flexible approach than the GRES tool provides. And right now, the GHG predicts GHG emission from 4 different pathways. Maud has already alluded to them. So ebullition, diffusion, degassing, and downstream emission. But it's important to realize that emission is only kind of the end product. It's the final outcome of a lot of biogeochemical processes that are occurring inside the reservoir. And I give just one example to illustrate how complicated it can be. So this is one reservoir, and the graph here is the surface is where it's 0, so the top is the surface of the reservoir, and 60 is 60 meters down in the reservoir. And on the x-axis here, you see the methane concentration. And this is a single reservoir at a given moment in time. And you can see that from the top, you have much lower concentration than at the bottom. And if you look at the x scale, this is a logarithmic scale, so there's a factor of 10 every time. So there's more than 1,000 times difference in concentration within a reservoir at a single point in time. And the importance of that is, of course, if you draw your water to be used in the generation of power that is fed through the turbine, if you draw that water from 25 meters or from 10 meters, you'll have nearly a 3 orders of magnitude difference in the concentration. And therefore, all that methane will be, if it's drawn from the deeper depth, then it will be released downstream once it has gone through the turbine. So it's very important to understand why is it that we can have such high differences within a single system. And such profiles, such complicated profiles, are the result of the interaction between the physics, the local climate, the biology, and the chemistry. So my contention here is that we have to understand what creates those very different patterns. And if we understand that, then we'll be able to ask what I call scenario questions. What if? What if the water level is changed? Can we minimize the overall GHG footprint through reservoir operation? And if so, when and where? What about pump storage or reservoirs in a cascade configuration? Can we model these sufficiently well such that we can kind of predict what would be the effect of pump storage or water level change? And we can also ask questions about how will the climate or global change affect reservoirs emissions in the future? How much has it already changed in the past? And to construct that, we are developing now, we're quite advanced in developing kind of a process-based model where we couple the physics and the biogeochemistry. And I won't bother you with the equation. It's not important for this purpose here. But basically what we're showing is that that type of model mimics quite well what the GRES tool itself is telling us, even though they're completely built differently with a different philosophy. But you can see that the two give comparable estimations, but this process-based model will allow us to answer the kind of question that I illustrated before. What's going to happen if we change water level? What do we do if we change the depth of the water intake, etc.? So this is in progress. And to further validate this new model, we are leading a project with a whole bunch of partners here in Canada, where we've measured 18 reservoirs. We just finished the last campaign on these reservoirs. So 18 reservoirs that we've visited for 3 weeks at a total. And this project has two main goals. It's to develop kind of a Canadian GRES version, more adapted to the Canadian landscape and climate, and also acquire the detailed empirical data to validate and calibrate the PB-RES model, that is this process-based model that I just described. So with this, I will leave you and thank you for listening to my little presentation.
Many thanks, Yves, for that. The next speaker in our talks has already been introduced, but I think it's worth emphasizing once again, briefly, all the work that Francisco's done to develop this webinar series, along with the other activities he does for ICOLD. So with that, please, Paco, back to you. Thank you.
Thank you, Steve. Thank you very much. Good morning, everyone. I will try to catch up a bit of the time. Next, I will present our ongoing research at ICOLD on a method for accounting for greenhouse gas emissions generated during dam construction. First, I will present the items that have been identified as the main sources of emissions. Then I will briefly explain the accounting methodology itself. And finally, I will conclude with a comparative example between various types of dams. This is the cover of the bulletin we are preparing at ICOLD Technical Committee D on emissions in the construction of concrete dams. We expect it to be published next year, and the aim is to identify ways to reduce emissions, as our dam construction activity must be, of course, part of this global challenge. To begin with, we have identified those resources used in dam construction that have the largest carbon footprint. The main one is cement, whose production is estimated to generate around 7% of all global emissions. But we are also considering other materials, such as the supply of supplementary cementitious materials, the production of aggregates, and other materials. Another significant source of emissions is the fixed plants installed on site for the production, transport, and cooling of concrete. Most of these plants run on electricity. The amount of emissions associated with the operation during the construction of the dam will obviously depend on the energy mix used to power them. The consumption of fuel for mobile equipment, most often diesel, is another significant source of emissions at construction sites. Finally, we are considering emissions caused by other resources at indirect construction activities, such as equipment of general use or general facilities, or, for example, the transport of workers and staff to the site. The methodology is built around 4 steps. The first step is to define a classification structure for the sub-activities, both at the organizational and operational levels. In this proposal, we consider the main contractor to be the entity ultimately responsible for emissions, whose optimization work is included in the preliminary construction planning, along with other traditional inputs such as costs or schedule. The second step, very important, is to create a database of emission factors applicable to the resources used in dam construction, paying particular attention to existing geographical and temporal differences. Here, for example, we can see the wide range of average emissions per country in the case of electricity, with some countries below 100 grams CO2 equivalent per kilowatt hour, and others with unit emissions that are 8 times higher. The calculation tool is based on the structure of the bill of quantities that is well known by designers and contractors for cost estimation. We will explain this in detail in a separate slide. The objective of the proposed methodology is not to carry out an exhaustive accounting of the emissions of all the resources required for the construction of the dam, but only those that have the greatest influence on GHG emissions. This covers between 80 and 90% of the total emissions resulting from the construction of the dam. The final of these 4 steps involves a critical analysis of the results, of course, to identify gaps and key factors contributing to emissions. It is possible also to make a sensitivity study by changing the value of those emission factors that are most unknown. This is the slide explaining the methodology itself. It uses the same calculation structure as for the construction costs based on unit prices and resource quantities for each activity, but using unit emission factors, as in column 5, for resources instead of their monetary cost. The total emissions associated with each type of resource are added up in column 6 for each item, and by adding them together, we obtain a total and unit emission per cubic meter, in this case of RCC concrete, as shown in this example. Using this methodology, we analyze here the example of a 112 meters high RCC dam, roller compacted concrete dam, with a typical high cementitious content. On the left are basic construction parameters, such as the duration, 24 months, the composition of the mixes, and a brief description of the main plants used for its construction. And this figure is the result. It represents the relative percentages of emission by type of resource. Those associated with materials account for almost 78%. Among these, type 1 cement accounts for more than half, despite its relatively low content of 87 kilogram per cubic meter. As indicated here, the unit emissions from construction in this particular case results in 155 kilograms of CO2 equivalent per cubic meter used in the dam. We have carried out this same exercise, but for 6 different types of dams with the same height and built on the same site. And this is a comparison between the traditional conventional concrete dam, for example, at the top, different types of roller compacted concrete dams, and in this second slide of summary, a concrete-faced rock-fill dam, for example, which is the one in the middle. And the one below is the most optimized gravity dam, which uses immersion vibrated RCC with only 60 kilograms per cubic meter of cement. So the partial results of these 2 slides, this is the first one, and the second, you have the total emissions, and you have the yellow marked with the ones per cubic meter of material used. I have a summary slide, which is this one, and this summarizes the results of unit emissions per cubic meter of dam material on the left, and the total emissions for each type of dam on the right. What we must take into account is not the lowest emission per cubic meter, as shown here on the left, but the total after multiplying it by the volume of the dam, which is shown in the figure on the right. We can see that the most economical, fastest to construct, and highest quality type immersion vibrated RCC is also the one with the lowest emissions of all types of dams. And some conclusions: what can we do to mitigate climate change in the construction of dams? First, to design to optimize and reduce the volume of the dam using the least possible amount of type 1 cement and maximizing construction efficiency. And what's next for the ICOLD Dams and Sustainability Initiative? We will continue developing this accounting methodology, improving the emission factors database, and sharing this exercise among the different technical committees of ICOLD for its validation. Okay, and that is the end of my presentation. Thank you very much. or your interest.
Great, thank you very much, Francisco. I can see there are now plenty of questions coming in, which is fantastic. I'm not sure if we will get through each of them, but what we plan to do, if that is the case, that there will be a short report published in the International Journal on Hydropower and Dams, and a free copy of that as a PDF will be available alongside the full recording of this webinar with the other two webinars. So please do keep the questions coming in, and after the last speaker, we will get through as many of those as possible. The next step in our talks today will focus on how some of the emissions Yves and others have highlighted might be captured, and sharing some of the latest industry innovations on this topic is Eliana Bohórquez-Bedoya. Eliana holds an environmental engineering and ecotechnology master's degree and also a PhD in natural sciences, with her research focusing on the dynamics of greenhouse gases in tropical reservoirs. As a research scientist at Bluemethane, she is actively researching greenhouse gases in liquid effluents and leading a key engineering project focused on deactivating methanogens and wastewater treatment plants. So over to you. Thank you, Eliana.
Thank you, Steve, for that nice introduction. Hello, everyone. So I'm sharing the screen.
You'll need to share the screen from your end, Eliana. There we go, perfect.
Yeah, okay, sorry. Okay, so yeah, are you seeing the screen now? Yes. Okay. Okay, yes. So we are going to talk about the journey from Bluemethane, from wastewater to reservoirs, and looking the potential of methane capture. So first, it is a funny title for this presentation because actually Bluemethane was born in hydropower dams. So the idea of capturing methane from water came actually from this article of The Guardian. The screenshot is there. One of the members of the team saw this and thought, okay, if hydropower dams are emitting greenhouse gases, between them methane, why not to look for a way to capture this methane and produce a new source of energy, if that is actually the business of hydropower, like produce energy. So yeah, but it's not only hydropower dams producing methane. There are other sources of water producing these gases. For example, industrial wastewater, municipal wastewater, biogas digestate, melting permafrost, or landfill leachate. So actually the company, when it was created, we realized that there is a broader field for this business, let's say. So actually, as I said, we started working in hydropower, and we saw the problem and the potential of becoming that problem into a solution. The thing was that in hydropower, we didn't get that much market traction. And the reason why that happened was that hydropower innovation is more towards the side of the industry looking for better efficiency or expansion or mechanical innovation, but not very much looking for new sources of energy. On the other side, there is also a lack of regulatories that work as a driver for motivating the methane capture in hydropower. So at that point, the company decided to shift the focus towards the industry with a regulatory driver and with a financial incentive to reduce methane from their liquid waste. This is the case of biogas operators, water utilities, and industrial wastewater treatment. Then we have been developing technology to capture methane from these liquid wastes, And we are now at commercial scale. The photo that you are seeing in your screen is our technology in that container, and it's installed in a biogas plant in the Isle of Wight in the UK. This plant converts agricultural material into biogas, and Bluemethane is putting even more biogas remaining in the liquid effluent of this digester in the system. So in that way, this improves the efficiency of the plant. Basically, our technology works using physics. So as you see, the water with methane comes from any source and goes through the system, then is flushed here, and then it passes through this part in which we apply a soft vacuum. And this differential pressure generates a first degassing of methane. Then the water or the liquid continues its way down to this spillway, in which there is some agitation generating turbulence and promoting the separation of the gas from the liquid. Then in the secondary separator, we refine that degassing to finally have an effluent of biogas and an effluent of the liquid. But the question of the potential of hydropower dams or for methane capturing, it remains. Well, our estimates say that we can prevent 1 billion tons of CO2 equivalent by capturing methane, including hydropower dams. The profiles that you are seeing here are from my PhD thesis. At Bluemethane, we don't have at the moment field measurements done by ourselves in reservoirs specifically. Of course, we have in other industries. But these profiles, what show us is what Yves Prairie just showed in his presentation as well. And it's that there are low concentrations of methane at the upper layers of the water column with probably oxic conditions, but close to the bottoms, we get actually interesting concentrations of methane for being captured. This concentration can be even close to the ones that we have measured in post-digested sludge. So as we needed data, we started to work in this project, Global Network of Greenhouse Gas Measurement in Hydropower, together with the International Hydropower Association and the University of Québec in Montreal. It's a first of its kind project because it's a decentralized measurement. What does it mean? Well, the project provides to the reservoirs, to the people there, training and sampling material. Then the people from reservoir go to the field, take the samples, and send the samples back to the laboratory in the University of Québec. And then the project goes back to these companies with a report of their estimates or measurements of greenhouse gases dissolved in water. 20 reservoirs worldwide are participating, and the approach of the project is a multi-seasonal measurement. This project was funded by the Global Methane Hub, by the way. And yeah, through this journey, we identified that there is a lack of financial incentives in the industry of hydropower. So this methane capture as a service works as a financial tool that removes CapEx requirement upfront by a reservoir owner. This was done together with Open Hydro, and it became with good estimates of the potential of the environmental and socioeconomic impact. with the values that you can see here. These are just some examples of these measurements. This report is on our webpage if you want to see it, and it's based on the Brazilian market specifically. So we expect, for example, that if we go from a proof of concept through a pilot and then a scale up, we need to mobilize a capital of $6.5 million. Then for a pilot, 54 million, and when we scale up, $3 billion. And we expect to capture between 500 tons per year during the proof of concept, and then when we scale up, we can go even up to more than 200,000 tons per year. And that is equivalent to 1.5 million cars emitting in a year. So as a conclusion, we can see that the technology is proven to capture methane from liquids in other sectors and can be used also in reservoirs, and that there are financial incentives that has been created to encourage the technology adoption. Thank you very much.
Thank you, Eliana, for sharing those really promising technologies. Now, the final presentation will bring together the various strands that we've been discussed and describe a decision-making system for calculating the carbon cycle at DAM project in China. Chuna Liu is professor at the China Institute of Water Resources and Hydropower Research, IWHR. She gained her PhD in 2013 from the Tsinghua University in China and has previously been a visiting scholar at the University of Michigan and Rutgers University, both in the USA. Her recent research includes establishing a quantitative model to evaluate carbon emissions at hydropower projects, including the identification of carbon emissions and intensity through different project stages. So thank you, Chuna. Can you hear us, Chuna? I think your mic.
Hello, hello.
Yeah, if you could share
okay, okay. Okay, can you see my screen?
Yeah, it's just loading this second. Yeah, we have it now. If you put it into presentation mode.
Okay.
Of water resources and hydropower research.
Wait a second. Okay. Hello, everyone. I'm Chuna Liu from China Institute of Water Resources and Hydropower Research. Today, I'm going to introduce the decision-making system for calculating the life cycle carbon footprint of dams in China. This speech will include 4 parts: the carbon challenge of hydropower in China, a life cycle assessment framework for dams, from calculation to decision, the support system, and finally, we will give some conclusion, limitation, and some prospects. Firstly, I will introduce the carbon challenging of hydropower in China. Regarding the carbon challenges, the emissions from hydropower projects mainly occur in 2 stages. During construction, the use of concrete, steel, fuel, and other generate emissions. During operation, organic matter from the catchment area, organic matter produced by the reservoir itself, and some decomposition of flooded plants and soil all lead to the carbon emissions. Against the backdrop of China's total annual GHG emissions from 1990 to 2022, the country has proposed the dual carbon goals: pink carbon emissions from 2030 and achieving the carbon neutrality before 2060. This demonstrates China's firm determination to promote green, low-carbon development and brings new opportunities and challenges to the hydropower industry. Now that we understand the carbon challenges in China, we will proceed to the second part, the life cycle assessment framework for dams. This study divides the dam life cycle into 4 stages. material production, transportation, construction, and operation. Carbon accounting for energy infrastructure is shifting from a production-centered perspective to a full life cycle perspective. When constructing the life cycle assessment framework, it is necessary to precisely set the system boundaries. During transportation, diesel and gasoline use generate carbon emissions. And during construction, consumption of materials such like cement, steel, and others, along with various construction procedures, also emit carbon emissions. During operation and maintenance, not only is energy consumed, but degradation of organic matter leads to emissions. Manufacturing processes also produce emissions. This section focuses on the system boundaries setting for the life cycle assessment of dams. First, aspects such as waste treatment, energy consumption, and fault handling during operation are listed. Then they are divided by stages, covering construction, early operation, stable operation, and decommissioning. GHG emission sources and related activities in each stage are clearly defined, laying the foundation for accurate carbon emission calculations throughout the dam's entire life cycle. In process-based life cycle assessment, a key formula is applied. This formula provides a scientific method for accurately calculating carbon emissions for hydropower plant dams throughout their life cycle. This section focuses on the selection of typical hydropower projects. Different types of dams are introduced, such as gravity dams and arch dams. Multiple adjustment models, such as daily and seasonal adjustment, are considered, along with various functions, including power generation and water supply. Here we get some key findings. Hydropower remains a low carbon source throughout its life cycle, with emissions stemming from 4 stages. During equipment manufacturing, emissions are derived from the carbon data of generating units and the installed capacity. Transportation covers emissions from moving construction methods and equipment. Construction phase emissions are calculated by the IPCC method for energy and material consumption. Finally, operation involves indirect maintenance emissions and direct releases from reservoir organic matter decomposition. Now let's employ emission allocation throughout the life cycle of a typical hydropower project. As indicated previously, carbon emission varies at different stages. Regional allocation of carbon emissions can accurately assess the hydropower project's carbon footprint and optimize each project stage accordingly, providing direction for achieving low carbon hydropower. In carbon emission allocation for typical hydropower projects, GHG emission factors show characteristics of being higher in construction stage than in operation and maintenance, and higher in production than in transportation. Research estimates the life cycle emission intensity at 3.51 grams of carbon dioxide equivalent per kilowatt hour, far below than the range reported by the International Atomic Energy Agency, demonstrating that the advantages of adapting to local conditions and the model in energy practice. Analysis of influencing factors on GHG emissions at different stages found correlations with reservoir age, storage capacity, water level, and installed capacity. Reservoir aging may alter biological activities and affect discharge. Large storage capacity and higher water level may increase the emissions due to the organic matter decomposition. Large installed capacity may lead to the more emissions during operation of equipment operation. And at different stages, significant correlation exists between GHG emission factors and the power density of hydropower projects. Higher power density means more electricity generated per unit space or resource. resulting in a lower emission factor. This indicates that increasing power density is an effective way to reduce carbon emissions from hydropower projects. After completing carbon emission calculation for hydropower, the key lies in converting it into decision-making basis, which requires a support system. We propose an integrated 4-tier system architecture. This 4-layer cycle of data collection, accounting, decision-making, display can seamlessly integrate carbon management throughout the DAM's entire life cycle. It acts as a bond, closely linking hydropower planning with dual carbon goals and facilitating the realization of low carbon hydropower planning. This system is powerful. Users can choose different stages, types, or passes as needed to quickly obtain the detailed calculation results and carbon emission intensity indicators. It integrates deep learning models such as TFT and predict emission trends and abnormal conditions by combining historical and real-time data. It is also equipped with a visual panel that dynamically displays key indicator and supports multi-dimensional queries and report exports. Additionally, the system supports multi-scenario simulation and comparison, helping users can assess the carbon footprint differences under different technical passes. Now we have reached the research summary. Our research integrates LC with the monitoring data to establish a national carbon emission factor framework and a decision support system, affirming hydropower's low carbon status and enabling strategy formulation. While there are still some limitations, such as overlooking soil carbon emissions, sampling spatial temporal differences, lack of nitrogen dioxide studies, and data limited accuracy. Addressing these gaps by focusing on soil carbon, improving samplings, and advancing nitrogen dioxide research is essential for future low carbon management. Okay, this sharing section is coming to an end. Thank you all for listening.
Okay, thank you very much, Tuna. So that concludes the presentation today, and thank you for very much for each of the speakers, and for ICOLD President Devendra Sharma at the beginning there for sharing his thoughts on the initiative. There's certainly a huge amount of work still to do and remaining for the ICOLD committees and the industry as a whole, I think, which is one of the main reasons we've been organising this series of webinars. I see there's plenty of questions already. We are a little bit behind schedule, but what we propose is to get through as many as we can do in the next 15 minutes or so, and then any which we won't have time for today, we will make a note of them and they will be given to the speakers. And as I say earlier, I hope to be able to publish them in the International Journal on Hydropower and Dams as a follow-up, and the PDF of that will appear alongside the free download of the recording of this webinar. So without further ado, let me start going through some of these questions. They cover all aspects, which is great. I mean, every issue which has been raised, there's further discussion available, I'm sure. So one, for example, here from Francois Halland to Marco Conrad. Do we have cases where the selection of the dam type, and the example of RCC versus CFRD is given, was driven by the greenhouse gas emission considerations? So in your experience, have any of your clients perhaps noted as one of the main factors in dam selection the emissions of that dam type?
Thank you for the question. Not as far as I know up to now. It's what we let's say encourage is that the GHG emission footprint should be part of a multiple criteria analysis as one of the criteria driving decisions. But to my knowledge, up to now, there has not been a project where a decision on dam type or project configuration has been based on greenhouse gas footprint results.
Okay. Now, perhaps that goes back to, I think, in your opening slide where you talked about there's a lack of legislation at the moment, or direct instructions for dam developers to have certain limits on the carbon intensity of them. Okay, and next question here. A couple of participants, in fact, have raised comments about reservoir sediments. Antoni Palau from the University of Lleida in Spain asks if reservoir emissions take into account the carbon fixed in the sediments, and perhaps Mold, if you're able to share your experience on this.
From my part, we do not measure carbon stock in sediments. We only measure water column gas concentration. Of course, if you work with a carbon budget of the entire watershed, sediments carbon stock will be included in the studies. But in the current way to calculate net emission, often it's not data that is collected on site. Maybe Yves could add some point on that topic too, because
Yes.
you need a lot of carbon estimate at the watershed scale.
Yes, very briefly. It's very tempting to think of sediment as kind of an offset to emissions. And one has to be very careful in doing that. And most of the times you cannot. And the reason for that is that the emissions, whatever sedimentation there was, is already embedded in the emissions. That is, if the carbon had not sedimented, you would have had higher emissions. So you cannot simply kind of do a subtraction of one the other to have a net. There are some cases where there's a portion of it that you can do. For example, if all the sediment is coming from the river and is sedimented in the reservoir, and that carbon would not have been sedimented somewhere else either in the sea or further down, then you could think of it as a trap, that kind of offset. But otherwise, if it's part of the biogeochemical cycle, most of the time you cannot subtract what is sedimented from what is emitted to get a net. So I just wanted to make that point.
Okay, thanks. Perhaps that leads to a question, Tuna, for you, where in your system, how do you define and perhaps limit, to make your work more manageable, the system boundaries when you're conducting life cycle carbon footprint assessment of dams?
Hello. Okay. Hello. Thank you, Steve. It means boundaries. Yeah.
Yes.
Yeah. And here in our research, we define the boundary from the material production, transportation, construction, operation. And during the operation stage, we've divided into early stage and to the stable stage. And the early stage, we've also for the two stages, we consider the maintenance and also some emissions from the reservoir. Yeah. So this is the boundary for our research.
Okay.
Yeah, and also Steve, yeah, I noticed that there is a question online about if we consider the GE tools to calculate the emissions from reservoir, because many professors mentioned it in this webinar. And I think in our research, we consider the total emissions, not the net emissions. So I will reply it online. Okay.
Okay, great. Thank you.
Thank you.
Another question here. For Eliana, please. Marco de Santos in Brazil mentions the concern there of unrelated anthropogenic sources that contribute with organic load to the reservoir, such as natural sewage discharges. I think Bluemethane, some of your technology has been applied at wastewater plants, so perhaps you could share some thoughts on this.
Yeah, but sorry, I don't get the question very well.
So as well as I think the natural bubbling of methane, I think they're talking about the sewage discharges into reservoirs and whether or not your technology is applicable to that as well.
Oh, I see. Well, our capturing technology, it's applicable as we can imagine that to be in reservoirs. It's applicable to dissolve methane in the water column. The bubbling, it's another problem. It's very difficult to model, to predict. It's very random, so that is not the target methane actually. But the inflows of wastewater into reservoirs or low quality water into reservoirs is like a problem, yes, and of course it contributes to the organic matter and all that in reservoirs. At the end, the capturing technology will be, as we imagine, located close to the dam to avoid like more the degassing part of the emissions.
Okay, there's a follow-up question here from Thomas Gaskell asking again, Eliana, what range of methane concentrations is economically viable for your technology? And I suppose in addition to that, could you share or give an idea of what percentage or what proportion of methane can be recovered?
Yes, we estimate good concentrations from 4 grams per cubic meter or milligram per liter and up to that. And about this second part of the question, which was
as a percentage?
Oh, the percentage, yes. We expect like half methane, half CO2, more or less. That is what we have seen in other industries, but and the efficiency around 50-something% for methane capturing.
Okay. 15, 15.
50.
50, okay.
Yeah.
Great. Okay, Maud, another question here for you. How do we convert the limited number of measurement points into an estimate of the emissions for the whole reservoir, given large spatial variability of the emissions? And that's from Francois Holland.
Yes, this is a good question. In fact, so I answered it in the chat that, of course, having just 3 sampling sites can be is very limited. That's why the work plan, the sampling plan that is discussed, this is prepared before going on site, is a very important step. In fact, we have to decide which site we will visit and to have the best representativity, if possible. Of course, in a small reservoir, it's easy, but in large reservoirs like we have here in Canada, it's tricky. It's right that 3 sampling station is not the best thing, even if that's what UNESCO guidelines propose. So this is something that we need to study side by side, in fact.
Sure. Okay, I can see there are plenty of questions coming in for Alejandra Bosch, who you'll remember was unable to join us live today. These questions will be passed on to her though, and as we mentioned before, a copy of all these questions I would hope would be available via the ICOLD website in the next few days, or at least in the next couple of weeks. One more question, Marco, for you here from Hamza at the University of Manchester in the UK. He asks, do the emission factors provide guidance for the use of high processing computer systems used for reservoir and embankment simulations for analysis during the design and refurbishment phases? I think this may go to the point of whether or not the electricity used in calculating project design is inputted, perhaps, I don't know, as a scope 2 emissions factor or something along those lines.
Yeah, I put a response into the chat to that question. Well, I understood whether it's generally required to tackle, let's say, the assessment with a high capacity computation or so. And my response was that no. I mean, it can be a simple spreadsheet analysis along the lines that Paco presented. I think it is much more important to really properly define boundary conditions, so the boundaries of the system, and the core infrastructure and the processes to cover the hotspots that possibly are identified in the analysis, and that's much more important. And looking at those hotspots, because that's the key to then come up with strategies and addressing the greenhouse gas mitigation.
Okay, great. Paco, Francisco, a question here for you. At what stage, and this comes up a lot at the Hydro conference in Greece just last month, where we had the session and some of these issues were raised. There were questions from the audience about which stage of the project is most useful to consider the methodology for calculating greenhouse gas emissions during the construction of a dam. So which stage should this work begin?
Okay, thank you, Steve, for the question. Thank you to the audience. Yeah, we see a very clear. There are three moments, I think, where these methodologies for calculating GHG emissions during construction will be fully interesting to use. The first one is in the very early planning stage, of course, when the owner has to take a decision on to build a dam or not to build a dam, and compare this situation from a global picture to have an estimate of what are the GHG emissions that the particular project he's thinking of will have. So it's very early in planning stage of the projects. Well, bank and other funding institutions will be for sure interested in knowing this kind of numbers. There is a second moment where I envisage there will be some interest in having these calculations, and that is exactly the time where we have to compare different scenarios in the design and construction methodology of the dam, when we are tendering and bidding for different solutions for the dam. And in this case, we can then be able, with the methodology, to compare different sizes of dam on the same site, or even compare different sites along the river, or put our GHG emissions input into the comparison of different types of the same place. So that will be another interesting moment. And the third one is obviously during construction itself, when we have already decided on the project and on the dam to be built. The methodology will for sure be a good tool to monitor where we are in GHG emissions actually during the construction, and compare that with the estimation that we might have done before. So I see these three moments, and I think it's a very interesting question. Where we point out about this? Thank you very much.
Actually, Paco, while you're still there, I have another question here from Lisa Benson. As has been demonstrated by some of the presentations, carbon capture technology exists, for example, in concrete and in plastic manufacturing. However, it's more expensive to use. And she talks about the green premiums. So perhaps Paco or anyone else who would like to talk on the subject of, is it true that to reduce the emissions, to make a greener project, that is necessarily going to be a more expensive project? And this is one of the main arguments coming out of COP, and perhaps why many leaders aren't there this week in Brazil, arguing that the priorities of their country are maybe short-term economic rather than longer-term sustainability. So would anyone have some thoughts to share on that?
I would leave probably Marco to comment on this, and I was just to mention that We have seen an example already where the lowest cost dam type has been also the lower emission dam type in our preliminary calculation, and only considering the dam and the construction of the dam. And of course, cost is a word that we have to properly apply and to understand what means cost and what is the age of this cost. No? Marco, you had also probably some comments on that. Thank you.
Yeah, briefly, the example that I presented, looking at feasibility stage at those two project options, RCC dam versus concrete face rockfill dam. Interestingly, in that project, based on the rough bill of quantities and the emission factors applied in the analysis, in that comparison, the lower carbon emissions also come along with the lower costs in that project. So the RCC dam was also, so the RCC dam project, let's say, with all the other components, was cheaper than the concrete face rockfill dam configuration, and also had the lower carbon footprint. And more generally, maybe a presentation that has been given at Hydro 2025 in Thessaloniki just recently from Landsvirkjun utility in Iceland. They presented their approach to tenders or to biddings in which they apply carbon prices. And in their findings, it is also the situation if the GHG emissions are internalized and like accounted for along with the price of CO2 certificates, for example, the project, including carbon mitigation, comes out at a lower overall internalized cost compared to a non-mitigated project. So that's quite interesting, but also shows the complexity of the issue in terms of cost.
Yeah. Okay. So potentially win-win projects. Okay. I think one more question for Yves, please. Do you expect that the new data collection techniques and modelling will change the GRES models substantively going forward?
Yes, I believe so. I think we're making steps to make sure that the new version, well, there's kind of the two advances that are going in parallel, right? The inclusion of new data and the development of the new model as well. And we hope that the new data will allow the inclusion of new variables in the GRES tool that were not that didn't come out in the first instance simply because we didn't have enough data to capture those. So I'm hoping that yes, the new data collected in the literature and the new data that we're collecting as part of our projects across Canada will improve both of the new model and as well as kind of the model of the new version of the GRES tool as it is currently understood.
Very good. Okay, well, unfortunately, I think we are out of time. I think the fact that we could go on for another hour or so is reflective of how good the presentations have been. So thank you again to each of the speakers. Paco will now just say a few words looking forward at the next steps of the initiative and also give some details on how you can contribute and get a copy of the outcomes of this meeting. So over to you. Thank you, Francisco.
Thank you, Steve. That's Paco is me. So sometimes you say Paco. That's my familiar name for friends. And thank you very much. And yes, we have to conclude. And it has been an amazing webinar. Very interesting questions. And thank you to all of you. So I have just prepared here some concluding remarks very briefly. Reducing GHG emissions is a commitment we must all make to reverse the trend of global warming. Dams and reservoirs are key infrastructures for adapting our lives to the effects of climate change. However, in addition to safety, which is a priority objective of dams, the construction and operation of these dams must be planned and implemented with the aim of mitigating climate change, that is, minimizing greenhouse gas emissions. At ICOLD, we are researching tools and methods, as this webinar is proving, that can be applied to the assessment of the life cycle carbon footprint of dams and reservoirs. In this webinar, we were fortunate to learn from international experts from different institutions about the work they are doing in this regard. Access to reliable data is essential, as we just heard just now, both for emissions produced in aquatic environments under different geographical and environmental conditions, and also for obtaining reliable emission factors for the resources used in the construction, operation, and maintenance of hydraulic structures. Please use this email address you will see now to send us other questions, feedback, comments, and suggestions to this webinar and to the ICOLD's DAMS and Sustainability Initiative. We will try to use also this email for answering the questions we could not answer today. And at this link, you can access the webinar videos of the past 2 webinars, where this one today will also be uploaded very soon. So you will have free access to this video from the webinar today. Finally, a big thank you to all the speakers for their time. Devendra, Steve, Alejandra, Marco, Maud, Yves, Francisco, Eliana, and Tuna. Thank you to all of you. Many thanks also to Hydropower and Dams, Steve and Spankle for their support. And many thanks, of course, to the audience for your interest and present and future contribution. Thank you very much and have a good day.
Thank you.
Bye-bye. Thank you. Bye.